Welcome to Spring LIB.
Okay, so for a Michelson interferometer, the key concept is that one fringe shift corresponds to a change in path length change of lambda, right? And so the number of fringe shifts n will be equal to the difference in the number of wavelengths in the two media, right? And so that is what we have to, and that is how we find the refractive index of the gas. So n, therefore, will be equal to, let me write this down first, n times d, n being the refractive index, d being the length of the cavity, over lambda the wavelength, minus d over lambda the wavelength. 2 out here is because the light enters the cavity twice. And for a cavity of length d, the number of wavelengths is d over lambda. Okay, and so in a different medium, that number is nd over lambda, n being the refractive index. Okay, so let's rearrange this. So this equation becomes 2d over lambda, taking d over lambda common, times n minus 1. And we can rearrange this equation to make small n, refractive index, the subject here. And so that's n times big N, number of fringe shifts, times lambda over d plus 1. And so fringe shifts is 176. Lambda is 632.8 times 10 to the negative 9 meters, 632.8 nanometers, over d, the length of the cavity. That's whoops, there'll be a 2 over here. So there'll be 2 times length of the cavity, which is 1.155 centimeters, so 1.155 times 10 to the negative 2 meters, plus 1, and this gives us 1.00482 for the refractive index.